Folks, I'm sorry to say I'm still not quite up to par, but we will proceed nevertheless. Regarding question 1912, which we looked at yesterday, which involved calculation of the solubility of calcium carbonate in water system buffered at pH 6. I think some of the arithmetic I put on the board was not particularly clear because I had not yet or yesterday recognized the need to do some recalculations based on the updated equilibrium constant information that's contained in our new information sheet. Because from the notes, you get, for example, the Ka value of hydrated CO2 of 4.2 times 10 to the minus 7, but the latest value I have is 4.5 times 10 to the minus 7. That's from the information sheet. And from the notes, we get a Kb value of bicarb of 2.4 times 10 to the minus 8, but the latest value is 2.2 times 10 to the minus 8. So to reiterate that calc, at pH 6, where what we have to do to solve this puzzle is to see how the bicarb molarity relates to S at equilibrium, recognizing that at pH 6, the molarity of carbonate ion means nothing. Material balance for carbonate-containing species at pH 6 is the sum of the molarities of hydrated CO2 plus carbonate ion that we looked at. So what we have to do is to see which are the principal forms of carbonate-containing things in the system at pH 6. And based on Ka for hydrated CO2 or Kb for bicarb, Kb bicarb, we can answer that question. Here's the chemical version of the equilibrium constant expression, which we want to rearrange in order to get a concentration ratio of these two forms of carbonate in the system at pH 6, for which the hydroxide ion molarity is this. So, hydroxide ion molarity divided by Kb gives us a numerical ratio of 0.45 to 1, showing us that in this solution at pH 6, this is the predominant form of carbonate-containing stuff, but this is also a form which has a concentration of significance. So, to get on with the relationship of bicarb to S, we rewrite S, set it equal to material balance for carbonate-containing things. Strike carbonate ion, because at pH 6 carbonate ion molarity means nothing. And from this, recognize that at 0.45 times the molarity of hydrated CO2 is bicarb ion. And if you divide this by 0.45, you see that this is equal to 2.2 bicarbs in this system at pH 6. So, we'll put in 2.2 bicarb for this, and that makes S equal to 3.2 bicarb. That's this, which means bicarb molarity is S divided by 3.2. So we've answered the question we need to answer. Put that in, solve for S, 2.0 times 10 to the minus 2 molar. I hope that clears up any lack of clarity which I may have made as part of this presentation yesterday. So we go to E. the last topic that you see in chapter 19. It should read, more on altering S by Bronsted-Lowry acid-base chemistry. What I think the notes state is alteration of S by chemical means. Well, this is clearly alteration of S by chemical means, but we've already looked at alteration of S by chemical means. For example, calcium carbonate solubility in straight water, calcium carbonate solubility in water solution buffered at pH 8, buffered at pH 6. Those are all altering solubilities, in that case of calcium carbonate, by chemical means, because we're changing pH. We looked also yesterday at the solubility of calcium hydroxide, calcium carbonate, calcium sulfate in solutions which were 10th molar in the anion component of the respective salts. Well, that's the chemical impact on solubility. So, I would like first, regarding this topic, that you examine the statement in bold on page 1913 in the notes. The statement says that if I am to consider the solubility of a salt of limited solubility in water in a solution which is more acidic than water itself, the solubility of the salt must increase unless this solution, which is more acidic than water itself, is a precipitator of the salt. Which means if the acidic solution contains a source of either the cation component or anion component of the salt, then the salt will be less soluble in that system rather than more soluble, even though the system is more acidic than straight water itself. Example taken from the notes. Solubility of calcium sulfate dihydrate, which we looked at yesterday, which you've investigated in lab. In sodium hydrogen sulfate solution, 1 molar. Well, if we want to consider the solubility of calcium sulfate in this system, we've got to get a handle on the sulfate ion concentration, because that's the component ion whose molarity we are concerned about. So, here's Ka, x squared over 1.0 minus x, solve it, x is 0.10. So, if I then look at the KSP expression for calcium sulfate itself, for which the value is 9.1 times 10 to the minus 6, I recognize that if I'm attempting to dissolve calcium sulfate in 1.0 molar sodium hydrogen sulfate solution, the solubility of calcium sulfate is still the calcium ion molarity, but it's not the sulfate ion molarity, because this sodium hydrogen sulfate solution has now been shown to show a sulfate ion molarity of 0.10. So I write this out, and I recognize at a glance, I hope, from an arithmetic standpoint, that whatever the value is for S to satisfy this equation, it's got to be a whole lot smaller than 0.10. Because the product of this number times this number has got to equal this number, and that's a pretty small number. Well, since this number cannot be smaller than 0.10, cannot be smaller than 0.10, this number cannot be bigger than 9.1 times 10 to the minus 5. Otherwise, this multiple won't equal that value. And 9.1 times 10 to the minus 5 is a heck of a lot smaller than 0.10. True. And then just as we did in 10th molar sodium sulfate solution yesterday. We find the solubility of calcium sulfate in the acidic sodium hydrogen sulfate solution to be 9.1 times 10 to the minus 5. How acidic is the sodium hydrogen sulfate solution? Hey, 1 molar. This is 10th molar in hydronium ion. That's pH of 1.00. That's pretty acidic. Yet this considerably acidic solution is a precipitator of calcium sulfate as opposed to being a dissolver of calcium sulfate because of the sulfate ion molarity which it contains. No, question 1913 is asking you if you see then how the solubility of calcium sulfate in our 10th molar sodium sulfate solution is the same as the solubility of calcium sulfate in our sodium hydrogen sulfate solution 1 molar. Same because this solution is also 10th molar in sulfate ion, just like this solution. That's what we just showed. Now let's get at the real nitty-gritty of this issue. Let's once again take a look at the solubility of our good friend calcium carbonate. This time in 1.0 molar ammonium chloride solution, for which the pH is 4.62. A good deal more acidic than straight water. So before we do any arithmetic, we can answer the question: how does the solubility of calcium carbonate in 1 molar ammonium chloride solution compared to this value? Remember that this is the calcium carbonate solubility in straight water? Okay. So how must the solubility in the ammonium chloride solution compare to this value? Does ammonium ion support the precipitation of calcium carbonate? Does chloride ion support the precipitation of calcium carbonate? No. And it's a solution which is more acidic than straight water. So the solubility of calcium carbonate in this system has got to be greater than this in straight water. Got to be bigger than this number. Now, is it going to be a whole lot bigger than this number? Don't be misled by that 4.62 pH. Why not? When I mix the calcium carbonate with the ammonium chloride solution, is the pH going to stay at 4.62? Is the ammonium chloride solution a buffer? Is the ammonium chloride solution a buffer? Is it a buffer? If it's going to be a buffer, it would also have to have a high molarity of ammonia. Does it have a high molarity of ammonia? Not hardly. Not a buffer. So what's going to happen to that pH when I mix calcium carbonate with the ammonium chloride solution? What's pH going to do? Sit there? Go down? Go up? Up! Because carbonate ion component of calcium carbonate is a base which is pretty strong as far as weak bases are concerned. Now then, in this system, here's the equilibrium reaction which will be established involving the material we are attempting to dissolve. So we write K. Recognize that this again is a K expression which is a composite of 2 or more simpler equilibria. What are the simpler equilibria of which this is composed? Well, let's let this thing talk to us. It's got calcium carbonate as a reactant. That means one of the component equilibria of this equilibrium reaction is what? KSP, calcium carbonate. So, I got calcium ion here. which requires me to add carbonate ion to put KSP calcium carbonate in here. So we did that. Usual technique, multiplication by 1, using appropriate terms so that we can see how our complex equilibrium relates to the fundamental equilibria of which it is composed. You see ammonium ion on this side reactant? Ammonia over there. What do you think in another is a fundamental K of which this equilibrium is composed? K of ammonia, Ka ammonium ion? How about Kb ammonia? How about 1 over Kb ammonia? Is that fair? Because ammonia is on the right as a product rather than a reactant, okay? And Ka ammonium ion interrelates the equilibrium molarities of ammonium ion and ammonia just like Kb ammonia does, okay? Now we also see bicarb as a product. Where's this bicarb coming from? By magic? Because the teacher put it in there to make the system perplexing? Or because chemistry's tough? Where's the bicarb coming from? Look at this reaction. Let it talk to you. Where's the bicarb coming from? Well, I start with carbonate ion as ion component of calcium carbonate, do I not? And if I want to make bicarb, I got a protonate carbonate. Well, what's my main protonator in this system? Ammonium ion, isn't it? But what I'm seeing is the conversion of carbonate to bicarbonate. Does that suggest another component K? Carbonate converts to bicarbonate. Kb carbonate? Does Kb carbonate involve the conversion of carbonate to bicarb? You're daggone right. Or how about bicarb, because that's a product for this reaction. How about bicarb converting to carbonate? Do I have a reaction which converts bicarb to carbonate? What's it called? What's it called? Ka of bicarb. Ka bicarb. But here bicarb's on the right. So that would be 1 over Ka bicarb, wouldn't it? No, I haven't written anything on the board. We're just letting this thing talk to us. Now, I know that's difficult for you. What I'm trying to do is to have you learn how to let this thing talk to you. It's tough. I'm very sympathetic with you. It's tough. But based on the K considerations we have so far made, everything we have just said follows. So, let's play this game. If I play this game, we've already checked these two terms. I just check the terms as I write down the corresponding K just for bookkeeping purposes. The terms checked so far correspond to the K which I've just written. All right? Now then, here's ammonium ion, reactant denominator, reacts with water. But if it reacts with water, ammonium ion makes hydronium ion. If I got hydronium ion in here? So instead I'm going to look at ammonia up top. And I'm going to remember what we just mentioned a moment ago about 1 over Kb ammonia. Because here's ammonia up top, here's ammonium ion down below, and here's hydroxide ion down below. Because when ammonia reacts with water, the products are ammonium ion and hydroxide ion, right? But I'm not looking at ammonia as a reactant. I'm looking at ammonia as a product. So the terms I've just checked, that correspond to Kb ammonia or 1 over Kb ammonia? 1 over KB. All right. So we'll put that in. And now let's examine the remaining terms. Carbonate denominator reactant, bicarb numerator product, hydroxide numerator product. What's that correspond to? KB carbonate? You betcha. Done. Notice that based on the bookkeeping, all the terms are now checked. They've all been accounted for. So I just put in the values, 6.2 times 10 to the minus 9, 2.1 times 10 to the minus 4, 1.8 times 10 to the minus 5, and push the buttons on my calculator. And get this. 7.2 times 10 to the minus 8. Now then, take a look at this number. As you take a look at this number, I'm going to write another number on the board. No, I'm not going to write it on the board because I've already written it on the board. Only it's this board. See that number? 7.2 times 10 to the minus 8. See this number? 1.3 times 10 to the minus 12. This number is for the equilibrium established when calcium carbonate reacts with what? With what? Water. This number reflects the equilibrium established when calcium carbonate reacts with ammonium ion, which guarantees, since ammonium ion is a stronger acid than water, that this K has got to be bigger than that K. We've seen that. Now let's take a look at the magnitude of the K itself. Does this K suggest that I can effectively dissolve calcium carbonate by hitting it with ammonium ion? Did that K over there, 1.3 times 10 to the minus 12, did that suggest that I effectively dissolve calcium carbonate by hitting it with water? Heck no. Look at the small solubilities we got. I mean, not the pH 6, because now we're not hitting it with straight water. We're hitting it with an acidic system, aren't we? If I hit calcium carbonate with straight water, what solubility do I get? It's 1.4 times 10 to the minus 10, isn't it? I mean 10 to the minus 4. 1.4 times 10 to the minus 4. Okay. So back to this K value. Does this suggest that I can effectively dissolve calcium carbonate by treatment with ammonium ion? Is this a big number? Not big at all. This is telling me, when this system comes to equilibrium, the concentration of this times the concentration of this times the concentration of this, the products for this reaction, divided by this reactant, is this tiny number. I'm not going to do much with calcium carbonate by hitting it with ammonium ion, but I'm going to do more to it compared to hitting it with water. That's about what these K's mean. Have we done a couple things with K's so far this term? A couple million things? You think we'll do some more? And then I'm sure you're sitting there saying, oh, I know damn well we're going to do a lot more. And you're right. Okay. 46L, assignment 3. After preparing calcium carbonate, by mixing calcium chloride solution with sodium carbonate solution. Remember doing that? Boom, out fell teacher's favorite weapon that didn't come out looking like this. You had to catch it and mold it and put a binder in there to shape it into chalk. Okay? But you made an immediate precipitation of calcium carbonate. And then you were asked to observe the solubility of calcium carbonate in various solvent systems. This is 46L, assignment 3. A recitation of the chemistry which you folks in fact did in this course. You were asked to attack calcium carbonate with 1 molar hydrochloric acid solution. What happened? What happened? Is that all that happened? Dissolved? Did you see bubbles? Alka-Seltzer reaction? You betcha. Anybody remember doing that in assignment 7 of 45 laboratory? Huh? You did it there. I know, that's ancient history. Teams of 3, little learning going on. Not your fault. I could ask Mr. Ritchie, who taught 45L last term, how many of his students from that lab course are in this gathering. Then for those who don't remember, I could blame him. But I won't do that, because it wouldn't be his fault. Then you were asked to take calcium carbonate and treat it with acetic acid solution 1 molar. This is back to 46L. What'd you find then? You couldn't have done this work too long ago. It shouldn't be that thoroughly removed from your memory banks. Calcium carbonate plus acetic acid solution. What happened? You got your acid-base table? Look at it right now. Let's go. Tell me how the acid strengths of acetic acid and hydrated CO2 compare. You're looking at the acid-base table. If you don't have the acid-base table with you, you owe me $10. And I'm going to stop. Before you go out today, everybody has to show me an acid-base table. He or she who cannot show me an acid-base table and has therefore not followed the directives I have said, which means you've got to have that thing with you all the time, $10. Or you're going to have to sleep in here overnight on this cold, hard floor. And I will not allow any pizza and beer to be shipped into you. Cruel, vicious treatment, wouldn't you say? Brutal. How do these two acids compare strength-wise? Acetic acid is a lot stronger, isn't it? If acetic acid is a good deal stronger than hydrated CO2, you should now recognize from what we did extensively in Chapter 18 that acetic acid is also an effective dissolver of calcium carbonate, like hydronium ion. Because it, like hydronium ion, is a good deal stronger acid than hydrated CO2, which means it can convert carbonate all the way to hydrated CO2, which, because of its instability, comes out of the system. And when it comes out of the system, you are effectively removing carbonate source from the system. Upshot, calcium carbonate quite soluble. Now let's look at ammonium ion, acid-base table. Ka ammonium ion versus Ka hydrated CO2. Which is a stronger acid? Hydrated CO2 by a good amount, wouldn't you say? Should be seeing 4.5 times 10 to minus 7 compared to 1.8 times 10 to minus, compared to 5.6 times 10 to minus 10. 4.5 times 10 to minus 7, that's hydrated CO2, versus 5.6 times 10 to minus 10 for ammonium ion, right? So hydrated CO2 is a lot stronger acid. Upshot. Ammonium ion can effectively convert carbonate to hydrogen carbonate, because ammonium ion is a good deal stronger acid than hydrogen carbonate. But can ammonium ion effectively convert carbonate to hydrated CO2? No. So bicarb is still in the system, and bicarb is a pretty good source of carbonate. Result, I'm not going to effectively dissolve calcium carbonate by treatment with any acid that is a weaker acid than what? Than hydrated CO2. We're attempting to take much of what we have been over so far and put it all together. Because when you get this chemistry together, then it makes elegant sense. That's when it's really fun. All right. Now then, for this system, we know that this is true. Because again, calcium ion, we put it in solution, doesn't do anything else. The question is, for this system, you think S is also equal to the bicarb molarity? You think it's close to equal to the bicarb molarity? You think S is equal to the ammonia molarity? Or close to the ammonia molarity? What do you think? Well, let's write this reaction equation. We just talked about the fact that this is a stronger acid than this, which therefore means that this is a stronger base than that. That means this is a large extent reaction. What numerical value can we now obtain that gives us a measure of extent? What is it? For a reaction, what numerical value assesses the extent of the reaction? What is it? What numerical value assesses the extent of this reaction? What numerical value assesses the extent of this reaction? What numerical value assesses the extent of calcium carbonate reacting with water? What is it? It's the K value, isn't it? All right. So if we want an idea about the ability of ammonium ion to attack carbonate ion successfully from a quantitative standpoint. We've already done it from a qual standpoint. We know this is a stronger acid than that. So without doing arithmetic, we know the K for this is bigger than 1. All right? We calculate K for this. You know how to do that. For this, K is on the order of 10. You do the arithmetic. You know how to do it. Now then, that means when carbonate reacts with ammonium ion, a main, if not exclusive, source of bicarb in this system is this reaction. Because ammonium ion is going to attack carbonate ion a whole lot more effectively than water. In that K value versus this K value. Okay? And another product of this reaction is ammonia. So do we expect this to be a stoichiometric statement? Do we expect it to be a fair statement that for this system, S, which we know is the calcium ion molarity, is also equal to or about equal to the bicarb molarity, equal to or about equal to this molarity? Let's do this. Is that fair? Let the chemistry talk to you. Because if this reaction for this system is the only source of consequence of bicarbonate and ammonia, an ammonium ion reacting with bicarbonate does not effectively convert bicarbonate to hydrated CO2, then what we've got here is true. Well, let's go forth on the basis of believing that what we got on the board is true. We're going to take it to be true, okay? I'll write that here. For now, we're going to take this as true. If we take this as true, how can we, in short order fashion, calculate the solubility of calcium carbonate in our 1 molar ammonium chloride solution? Because notice what we've taken to be true. Calcium ion molarity, bicarb molarity, ammonia molarity, all the same. So, based on this, we'll write this here. We get this. There's K.